Okay, hello everyone. Today I will introduce the red invariant extend common filter in 3D SLAM problem, including point feature base. And if I have time, I will also introduce something about RI-EKF for object-based SLAM. I will first review a general extend common filter framework. Then I will introduce red invariant EKF for 3D point feature based SLAM. And finally, I may introduce the red invariant EKF for object-based SLAM. At the beginning, consider a scenario that you are in an unknown environment with some new landmarks. Could you know where you are? If you stay stationary, could you make sure where you are in the global frame just by observing such new landmarks many times? The answer is no. The only thing you can get is the landmark's location in local frame. And as you observe those landmarks, you can estimate a very accurate location of them in local frame. But if the local frame is not 100% precise and it has some noise, the observations of landmarks cannot make any contributions in determination of local frame because their locations are all based on the local frame. So there should be some informations we cannot observe, and they will leave no impact on state estimations. However, an improper linearization such as standard EKF or called SO3 EKF could lead a bad performance in terms of convergence and consistency. Today, I will introduce red invariant EKF, which is a better linearization method for EKF SLAM. As Sheldon presented in the last week, extend common filter in SLAM considers the following forms of nonlinear dynamic models, including the process model and observation model. Okay. After some linearization, we can estimate the current state with uncertainty using its common filter. The uncertainty of a state is assumed as this form. It's a kind of Gaussian distribution in nonlinear space. The arrow E is of a zero mean Gaussian distribution. X hat is the mean estimate of X. The O plus here is some operator combining the mean and the arrow. It's also called retraction. The arrow vector can also be described by the inverse map of retraction, and the different retractions can determine different linearization approaches, which will significantly influence the result. Based on a selected retraction, we can compute the values of Jacobians in its EKF framework, as shown here. The equations are complex and confusing. I have a simpler way to compute these values by using Taylor series. It's the equivalent definition. The Jacobians of a function is a coefficient matrix of the first order error and noise. It becomes much easier. And due to the different retraction, the forms of errors are different, leading to the different Jacobians. Now come to 3D point feature-based SIM. The considered state vector combines the rotation and position of the robot and the positions of observed features. The rotation belongs to SO3 and all the position vector belongs to R3. The process model is shown here. The robot pose moves via the odometry and the feature remains stationary. The considered observation measurements are the relative feature positions in the robot frame. This is a very simple model, and the bearing and ranging function can also be considered. They are the functions of the relative feature position. But the further conclusion are the same. So for simplicity, the observation measurements are set as here. The conclusion is similar. In this section, standard and ret invariant EKF will be introduced, and then convergence and consistency will be further analyzed. As we discussed in the previous section, the retraction will determine the linearization approach. The retraction in SO3 EKF is very simple and seem naturally. You can see that the position parts are linear. The arrows of but there's no free lunch. The linearization, this linearization could not remain some invariance of SLAM system and perform bad in terms of convergence and consistency. This will be discussed later. The ret invariant EKF is based on a Lie group. A state vector are shown in the left, and we can equate this state vector with the square matrix in the right. The square matrix is n plus 4 by n plus 4 by n plus 4. Denotes the handwriting G to be the set containing all state vectors. We call this the state space. And we denote SE n plus 1 to be the set containing all the square matrix, like in this form. And because we equate the state vector to the matrix in the right, we can equate the G with SE n plus 1. And then we can prove that SE n plus 1 is a Lie group under matrix multiplication. And for a Lie group, there exists a unique exponential map which transfers the tangent vector into a group element. The statistical model of X is generated by the right invariant tangent vector field because the geometry near any point in the Lie group is the same as that of the unit element. So we just need to investigate the tangent vector or the arrows near the unit element, and we can multiply a group element. Then we can get the arrow space near the group element. This is something like the right invariant tangent vector field. And I think the right invariant here in the name is from the right invariant tangent vector field. Actually, the structure of SO3-EKF is also a Lie group, but it is very trivial and does not compatible to the SLAM problem. In contrast, right invariant EKF is more proper to the considered SLAM problem. Based on the special Lie group, the retraction of right invariant EKF is defined as follows. It looks more complex than SO3-EKF. When we focus on the arrow components of position parts, we can find that this part of right invariant is nonlinear, but SO3-EKF, this is linear. The nonlinearity of right invariant EKF is compatible with a SLAM problem. The Jacobians is more simple than standard EKF because right invariant EKF transfer the model's nonlinearity to the nonlinearity of the arrow.
Yang, can I ask you a question? What is FK and FK?
FK is the FK with brief is the real position of the features, and FK is the estimate positions of features.
So this is a error of the feature estimates, right?
Right. So it's nonlinearity, and it transfers nonlinearity of the models to the arrows. So it makes the Jacobians more simple and have more good properties. Right.
So so for the FK is in the global frame, right?
Right.
And FK with the brave or whatever is in a, can we say it's in local frame? No.
No, they are in the global frame. Sorry.
So they're all in global frame, right?
Right. Right.
Okay. Keep going.
Okay. So as a result, right invariant EKF can outperform SO3-EKF in terms of convergence and consistency. Shoudong have analyzed the convergence of standard EKF in 2D case, and 3D case is similar. When a robot remains stationary and observe a landmark many times, it should converge to P, the covariance should converge to P infinity here. And we should know that the uncertainty of RoboPose should remain unchanged in the whole process. And we cannot correct the current RoboPose as well. Just like what I introduced at the beginning. we can only observe the relative position of the features, and this relative in the local frame, and this relative measurements cannot crack the local frame and make no contributions to the robot estimation. However, the experiment results illustrates that uncertainty of robopause in RI-EKF will not be reduced by observing such relative measurements, but SO3-EKF, you can see that it will reduce the uncertainty of robopause, and also it will the robot angles is changing. I checked some papers, and I think if the SO3-EKF, the Jacobians evaluate at the ground truth, standard EKF should also have these good properties. It's impossible to evaluate it as a ground truth. However, right invariant EKF can naturally have these good properties. This is the advantages of right invariant EKF in SLAM problem. Right. In the scenario that robot remains stationary and observe landmark many times, and then take a step to observe the landmarks many times, the uncertainty will be reduced to a lower bound, but the bound of robopause is not lower than the initial uncertainty. The experiments validates the better convergence properties of right invariant EKF. In the consistency analysis, I will introduce the reasons why right invariant EKF perform better than SO3-EKF. Some problems should be equivalent under the following stochastic rigid body transformation. We first look at this definition. Such kind of transformation can be divided into deterministic rigid body transformation and stochastic identity transformation. Actually, standard EKF and right invariant EKF are both invariant under the determinist rigid body transformation, but standard EKF, SO3-EKF, is not invariant under stochastic identity transformation. This will cause some problem. The stochastic identity transformation is something like that. And how to understand this invariance? If we have a SLAM system, one time we set x0, p0 as the initial. Another time we transfer this initial to y0, p0y by such a transformation. it is something that, like we just change the global coordinate. So after any times of motion and observations, the estimations should keep these transformations. But SO3-EKF is now invariant under stochastic identity transformation, and RI-EKF is invariant under stochastic rigid body transformation. The invariance of stochastic identity transformation.
Yang, can you go back to the previous slides? Yeah. Right. So what's the first row P0Y? What does that mean? P0Y.
P0Y is the uncertainty of the covariance of Y0. When you transform X0 to Y0, and the corresponding uncertainty should also be transferred, and the transform relationship is by P0 to P0Y. It should have this two relationship.
Yeah, and X and hat and Pn is estimate and the correct matrix at step n, right?
Right.
So that's from something like Kalman filter.
No, this is from the system, SAM system. The SAM system should have these good properties. And standard EKF and invariant EKF is to estimate approaches. If a good filter should maintain this good this eccentric properties of SAM system.
So that the stochastic identity is related to Q2 part, right? Q2 sigma,
right.
Q2 transverse, right?
It's correct. It's something like we change the global coordinates, and so we also need to change the covariance. And invariance of stochastic rigid body transformation is eccentric in the SAM system, because this transformation cannot be observed in the system. So it should provide no information in the estimation of states.
So what is Q1 and Q2 here?
Q1 and Q2 is the Jacobians of this transform T.
Okay.
Okay. So if we have the invariance of stochastic identity transformation can also be viewed as observability constraints. The observability matrix is defined as follows. The unobservable subspace is denoted as N, and it is the null space of observability matrix. The notations with head are based on estimations, and the notations with spring are based on the ground truth. A consistent filter, something like a good filter, should maintain the observability constraints as follows. The unobservable subspace based on estimations should be same with based on ground truth. We can check the Std-EKF for point feature baseline does not maintain such constraints. This shows Std-EKF obtains superior information, making its estimation more inaccurate. But the Std-EKF itself saw that it got more correct information and thus lower the covariance. Finally, Std-EKF underestimate the uncertainty, leading to the inconsistency. To test inconsistency in simulations, we usually use NEES indicator, which is defined as follows. M is the numbers of Monte Carlo runs. D is the length of arrows, arrow vector EI. PI is the corresponding estimate covariance. By statistical theory, the values of NES should near 1 for large M if the estimator is consistent. In an experiment, the robot moves in a 3D invariant with 300 landmarks. RI-EKF performed better in terms accuracy and consistency than the Std-EKF. So, okay, we have time. So now we have known that RI-EKF perform better than Std-EKF in point feature-based set. Because RI-EKF is invariant to stochastic rigid body transformation, it naturally maintains the observability constraints compared to SO3-EKF. It doesn't obtain superior information in the unobservable directions. As a result, RI-EKF improves the consistency. Now, we can also generate this RI-EKF into object-based style. First, we can introduce something about object-based style. With the recent advance of deep learning techniques, we can detect the object features. And object features considering the eccentric constraint among low-level features, such as point features. And it contains more information. And in many research, the SLAM problems using object features have some good properties, better properties than just using the low-level feature. So this is our work submitted to RIL this year, and we introduced a new Lie group, and based on this new Lie group, we proposed RI-EKF, and it has similar good properties like RI-EKF in point feature-based type. The object feature considered here, is shown here. It contains the rotations and positions of the feature. It's a pose of the feature. And the pose of object feature is something like that. This is an image from the real data. And using those point clouds, we can use deep learning method to estimate the relative pose of such object. And sometimes, and they will have noise and sometimes outliers, like this one. The state vector is shown here, containing the rotations of robots and features, and contains the positions of robots and features. The rotations are belongs to SO3, and position vector belongs to R3. The process model and observation model are shown here. The process model is similar to the point feature based type. Just there's also the rotation of features more than the point side. And the observation models is not the relative positions, but the relative pose of the features. It's more nonlinear. And standard EKF, the linearization of standard EKF are shown here. The eta here is arrows of standard EKF. It's something you can see the positions of the position parts are also linear, and the rotation part is just some linear in SO3. And right invariant EKF is based on the proposed Lie group structure. The O plus here is the Lie group multiplication. And based on such Lie group, the arrow state is shown here. The exponential map is something like the right invariant EKF in point feature based set. And here is uncertainty of a state. And we can analyze observability for standard EKF and RI-EKF. And we find that standard EKF also cannot maintain observability constraints, but right invariant EKF can naturally maintain this observability constraints, and it have more good properties in accuracy and consistency. We also test the proposed method in real data set. We select 4 real data sequence and using deep learning method to get a relative pose, and use our right invariant EKF, combining the constant velocity model and outlier removal to estimate the current robopose object pose. The results are shown here. The robust RI-EKF perform the best, and we also compare to DVO and RBSM2. It is also better than these two optimization-based method. I think the reasons that why RI-EKF is better than these two optimization method is that these two optimization method just use the low-level features, the point features. They did not use the object features. So the informations are different. So these two experiments validates the efficiency of our proposed method and the potentials of our method. In summary, RI-EKF is based on a special Lie group, SE n+1, or some variants of this Lie group. And RI-EKF can naturally maintain the correct unobservable subspace and do not contain the spurious information in unobservable directions. And finally, RI-EKF improves the consistency. That's all for my presentation. Thank you. Okay.
Thanks, Yang. For the results of the practical data set, you compare with RB SLAM.
Right.
So can you, because even the standard EKF sometimes is better than ORB or DVO, right?
Right.
Yeah, so what did you say? You said the point, one is using point feature, one is using object feature, right? So why EKF is better than optimization here?
Right, right. Because optimization based use a point feature based SLAM, but the standard and RI-Invariant EKF use object based SLAM.
But why using object is better than using points?
I think because the object feature contains all the how to say, contains all the informations of this point cloud, and I think it's more. It can have more lower noise level about this about the object observation. But the point feature, for example, maybe at one frame you can see this point, but at the next frame this point feature cannot be detected. However, the object feature, you can see them all the time. Maybe this is the reason. And I think the advantages of object and over the point features should also be invested in the future.
Can we say in the object feature-based SLAM, we have more constraints. For example, if there are like 4 points on an object, so just imagine you have like 4 corners of an object, right? Then in the object-based SLAM, we have the constraints saying those 4 points need to have a kind of particular rigid structure because it's on an object. But for the point feature-based SLAM, those 4 points can be arbitrary. After your estimation, those 4 points doesn't need to be forming a rectangle or something, right? But for the object-based one, we kind of say there are some constraints here.
I think so. And I think consider such constraints. The object features consider all the point features, and as a result, I think the noise level of object feature is somehow linear, somehow lower than the just consider 1 point features. So the observation is more accurate than point feature, than consider all the point features. That's my understanding. Because you consider the eccentric constraints, just like you say, the corners, the rigid constraints.
Hi, Yang. I have a question. So is a object-based, they consider the relationship between the points and the points, or just separate? Is a point-based just point and point, they don't have the relationship, but the object-based, they have the relationship between the points between one object. Is that right?
Right. I think.
So that's why it's accurate.
Right.
So you
actually, I think what I said might be not completely true, but I don't think for the object level SLAM they consider the individual points. But when you detect the objects, you kind of have those assumptions. This is one object, that's the same object, then they have the same structure. But in the EKF algorithm itself, there's no points there, right?
Right.
Yang, so thanks for your presentation. So could you please go back to somewhere at the very beginning that you're introducing the traditional way of solving EKF? I can't really remember which page. Then you mentioned the Jacobian.
Okay.
No, maybe before. Yeah, I think that's page 9. Yeah, I have. I'm not an expert in EKF, as I think most of you know. So, sorry, the previous page. Yeah. So in here, the Fn, Gn, and the Hn are the Jacobians, right?
Right.
Yeah, and can you explain why there is an O minus on Fn and Gn, and there's no O minus on Hn?
Well.
Yeah, why I'm asking this is because your Jacobian, I think, is a bit different from what I found in Sheldon's EKF tutorial.
Yeah. I think there's a mistake.
It should be an O minus, right?
Right. There should be an O minus.
Okay, then my question is why there's an O minus?
O minus is well,
in the traditional way, I think in Sheldon's EKF EKF tutorial, it seems like you just do a partial derivative with respect to the error or with respect to the state, and that's it, right? It doesn't have to give a O minus, but I don't know why there is O minus here.
wow. Let me think. Let me check. Wow.
Can I think that's because of the motion model, right? It's just the transform, that's the operation that transform from the previous to the next one, is it not?
I think the F, the function F is the motion model, right?
Right. F is.
And normally we just calculate the Jacobian of F with respect to X and also with respect to W. Normally.
Yeah, I'm following you. But what I think it's they are putting explicitly the F.
Yeah. So why there's O minus
to...
the what is that? The X hat one or FX hat. That's my question.
I think.
Yeah, no idea of that notation.
In my understanding, it's notations, but these two notations are not consistent here. We should correct them.
So how about your next page? I think the next page you are using a different way to do it, right?
Right, but the values of them are the coefficient matrix of the first order, and this is just because the derivations is on the nonlinear space, so the notations may be confusing. Well, where is O plus, O minus, and derive D here. So it's just means that we derive the observation function by the ROE, and here is the epsilon here and the ROE. I think it's just notations, but maybe it should be consistent.
Hey, thanks, Yang. I think I have to derive it by myself, and then
if you follow this page, your current page here, we should be able to get F and G and Hn plus 1 as well, right?
Right. I usually use this one. Okay. The paper, this is showing in the paper, and I also be confused by the forms, so I use another definitions.
Okay.
Yeah. Yang, if you don't mind, I will ask my second question. Can you go back to page 17?
17. This one.
Yes. So could you please explain a little bit why in H the derivative? Yes. Why the derivative of with respect to the that should be the rotation, right? Is 0. Normally it shouldn't be, right?
It should be 0 for right invariant EKF, because you can see the linearization about the position here, so position part. It contains some information of the rotation arrow, and the H is the Jacobians of observation model, right? And the observation is relative position in local frame. And right invariant EKF, this spatial linearization can how to say it's compatible to these measurements.
Yeah, so I may be quite stupid in EKF because I think nearly all of my works are not on EKF. But I mean, in my feeling, it's like the H you have, the Jacobian H you have, it's the same as, it's similar or nearly all the same as what we have in the least square based SLAM, right? Because it's about the Jacobian of the observation, right? And then I can see that, yeah, I can see your minus R transport and R transport are the Jacobians with respect to the feature location and also the translation, right? So the first one is translation, the second one is the feature. So in the optimization, if your Jacobian is 0, means this observation is not have nothing related to that variable, but it shouldn't be that case in SLAM, right? So I'm still like a bit confusing about why this is 0.
I think because maybe because the related measurements in local frame how to say may do no contributions to the rotation of the current robot rotation. But I didn't thought that, you know, I just use some functions, derive these functions to compute the Jacobians. But I'm not very clear about the zero of rotation parts. The contributions of 0 parts of Jacobians will lead to the estimation. But we can derive this Jacobians here. The observation functions is the relative position, right? And
yeah,
it's equals to R transpose hat. Hat means estimation and exponential of minus E theta, right? And multiply F plus DF. DF means F. Oh, sorry. Means DF hat F minus F hat minus P minus DP, right? And we can find that EK approximate F brief minus exponential E theta, and I think this is minus
Yeah, I think maybe you can do it later. But if you can help to derive this H Jacobian. For a simple example, maybe just a one post, one feature. That will help a lot.
Yeah. I think it's too complicated for me now. So maybe like we can like try to derive it from for a simple case that will be really helpful to understand. Yes, thanks, Yang.
Thank you.
Any other questions from others? Yeah, if not, probably we can finish the presentation today. Thanks, Liang, a lot.
Thanks, Yang.